Next, we're going to talk about the analysis of path length in binary trees. And this is an important problem to study because that's the quantity that we use to predict performance in the analysis of the binary search algorithm that I talked about before. So here's the definition that I gave before for a binary tree in the level and the depth. When we talk about path length, what we want to compute is the average length of a path to a node that's in the tree, say an internal node. So to do that, we compute the total internal path length, and then dividing that by n gives that average cost. And so to compute the total, you just count the number of nodes at each level. So at level 1, there's 2 nodes. At level 2, there's 4. Level 3, there's 3. 4, there's 1. 5, there's 1. And you add that all up. That's called the internal path length of a binary tree. It's the sum over all nodes of length of the path from the root to that node, or the sum of k times the number at depth k. For binary trees, we also talk about external path length, and that's just the same thing for external nodes. External, and also that's a quantity of interest in studying the binary search algorithm. These things, there's relationships among these that are easy to prove. It's all recursive. And there's a lot of notation to be able to talk about these things. So let's look at some simple relationships among them. So we're talking about binary trees, and we have the size function, and just a different size function for external nodes. And then its left and right subtrees will indicate with TL and TR. IPL stands for the internal path length. XPL stands for the external path length. So that's all the notation. And again, these are simple quantities to define, as I did on the previous slide. So here's some recursive relationships. So one thing is the number of internal nodes in a tree is the number of internal nodes on the left plus the number of internal nodes on the right plus 1 for the root. So that's fine. External nodes, it's just the root is not an external node, so the number of external nodes in the tree is the number of external nodes on the left plus the number of external nodes on the right. Internal path length, so this is an interesting one. If you wanted the internal path length of the whole tree, you take the internal path length on the left and the internal path length on the right and add those together. And then what you are is you're off by 1 on every single node except the root. So if you add t minus 1, then you're adding this link to all the nodes. And so that's a recursive relationship for the external path length. And for internal path length. And for external path length, it's similar. External path length on the left, external path length on the right, but you're off by 1 for every node because you didn't take into account the nodes that connect the external node, the subtrees to the root. So those are simple but very useful recursive relationships. And then from those relationships you can prove easy things like the number of external nodes is equal to the number of internal nodes plus 1. And that's just by induction. So just plug in from this formula here, the number of external nodes is the sum of the external nodes in the two parts. By the inductive hypothesis, that's equal to TL plus 1 plus TR plus 1. And then using the recursive relationship for internal nodes, we're left with internal nodes plus 1. There's lots of ways to prove that. Here's another one. External path length is equal to internal path length plus 2 times the number of internal nodes in the tree. And again, that's inductive right from the simple recursive relationships that we talked about. And again, there's a lot of ways to prove those things too. Just using these as an exercise for getting used to the idea of path length and its relationship of the path length in the subtrees to the path length in the whole tree. That is critical to the analysis that we're going to do. Okay, so here's our first problem, we have a random binary tree. So that's a binary tree where all tree shapes are equally likely with probability 1 over Catalan numbers 1 over n plus 1, 2n, choose n. What's the average path length of a random binary tree? That's some kind of description of the tree shapes that we saw. How far are all the nodes from the root? How far is an average node from the root is sort of what we're saying with that. These are the quantities that we're going to work with. So Qnk is the number of trees with n nodes and internal path length k. Tn is the number of trees, that's the Catalan numbers. And the accumulated cost is the total internal path length on all trees, so that we get the average by dividing the accumulated cost by the number of trees. That's the way that we compute average values of parameters. So this is for 2. In this case, both of the trees with 2 nodes have internal path length 1. So the average, so the total accumulated internal path length is 1. The average internal path length is 1. It's still not so interesting. Now this is a little more interesting. There's 5 trees with 3 nodes. 4 of them have internal path length 3. 0 to the root, 1 to the one below, and 2 more to the next one. So that's 3. 4 of them have that structure. 1 of them has internal path length 2. The nodes are both just 1 from the root. So Q3 2 equals 1. There's 1 tree of size 2 that has internal path length 1. And there's 4 trees of size 3 that have internal path length 3. And that's a Bogus T3 equals 5. So the average internal path length is 14 over 5 is 2.8. So that's the figures for 3, and here's the corresponding figures for 4. Total path length in all of these trees is 74, and there's 14 of them, so the average expected internal path length is 5.2 in these trees of size 4. And then you can take that and say the average distance to an internal node, divide that by 4 again to get about how far a node is from the root. So that's the quantities that we're after. Now it's always good to do small cases like this to make sure that you have a good fix on the exact quantities that you're analyzing. Expected path length of a random binary tree. Here's the analytic combinatorics derivation of this, and these are all things we've defined so far. The counting GF is just the Catalans. And so that's all the information we know about the Catalan numbers. The cumulative cost generating function is sum over all trees, internal path length times z to the tree size. That's also equal to the sum on n, sum on k number of path length k, and so forth. But from now on, we're just going to go with cumulative counting. And we know that the average is going to be the coefficient of z to the n in the q divided by the coefficient of z to the n in the t. The coefficient of z to the n in the q is the total internal path length of all trees of size n. If you divide that by the number of trees of size n, then you get the average internal path length. So that's the cumulative counting method that we're going to use to analyze this quantity. And so now what we have to do is analyze that cumulative cost generating function, and that's what we'll do next. We have the counting GF and we have the cumulative GF, and we're going to use this recursive relationship, slightly different but pretty similar to the one that we just talked about. The internal path length of a tree is equal to the internal path length of its 2 subtrees plus the number of nodes in the 2 subtrees. From that definition, we can immediately write down this decomposition. This first one is for the empty tree, and this other one is for the root. But if we have that function, we look at this decomposition, IPL of t is exactly equal to that, and the size of t is exactly equal to that. So we have that double sum for the cumulative cost. In that decomposition, or looking other way, that construction, now we can rearrange terms. And you can see, for example, that IPL TL Z to TL times Z to VR, that's Q of Z, T of Z. So that's one of the terms that we find in there. And the other ones where these TLs come into effect, we get T prime of Z, T of Z. This formula has those four terms, and using these two equations, it immediately reduces to that simple equation relating the counting generating function and the cumulative generating function. Recursive equation that relates those two generating functions. Extremely simple argument. It's actually possible to develop this symbolically, and we'll talk about derivations like that in part 2, but it's worthwhile having the explicit decomposition in front of us to see how directly we get to the equation that matters, which is the equation relating the generating functions that we can then solve and analyze. Okay, so just to get it all on one slide, I'll put those steps down here. So now we know that Q of Z equals 2 of Z T of Z times Q of Z plus Z T prime. We know what T and T prime are. The only thing we don't know is Q. So we can solve that for Q. And then we can just, T of Z, remember that's the Catalan, and we know what T sub n is. And T prime is just the derivative of that, which has two terms in it. But there is one thing that simplifies calculations a lot. 1 minus 2Z T of Z, if you multiply this by 2Z, it's just square root of 1 minus 4Z. So that takes care of the denominator. So there is still a little bit of algebra multiplying these two things together. But there's lots of cancellations because square root of 1 minus 4Z times square root of 1 minus 4Z is just 1 minus 4Z. So I'm not going to pretend I'm going to omit some of the algebra. But the final result is pretty simple. So that's an explicit equation for the cumulative counting generating function. And what do we need? The coefficient of Z to the n in that is the internal path length of all the trees of size n. Just looking at that, you can see that it's going to be 4 to the n. Next term is lower in magnitude. Take all those binary trees as Catalan numbers and add up all their internal path lengths, and you get 4 to the n. It's surprisingly simple. It's not exactly 4 to the n, but asymptotically it's 4 to the n. And that's why we want to do precise asymptotics before. Because if you take that and divide it by the Catalan, all you're left with is n squared root of pi n. We divided two huge quantities, but since we were working with precise asymptotic results, we get a precise answer. The average internal path length of a random binary tree is asymptotic to n square root of pi n. And that's a very accurate estimate for the average internal path length. And we could do it, we could get it exactly, but doing it asymptotically is very compelling because it's a simple and surprising and unexpected result. Now let's look at the same thing for random binary search trees. So that one it kind of explains or starts to explain the shape of a Catalan tree. The nodes go down square root of n, which in a 10,000 node tree goes down 100. It's a pretty good size depth, and that's average, so it goes down a few hundred. What about binary search trees? Well, here's the same calculation for binary search trees, but now we're counting permutations that result in a binary search tree with n nodes and internal path length k. Now it's a little easy because the counting factor is n factorial, we know that, but still the accumulated cost is the same way. It's just that we have to count the number of permutations. So in this case, some of the trees have internal path length 4, 5, and 6 as before, but the weighting is different. So all of these 12 permutations give 4. there's only 4 of them that give 5. That's these 4. And the remaining 8 give 6. So the total internal path length of the trees that you get from all of the 24 permutations is 74. If you divide that by 24, you get 4.833, which is less than what you get for Catalan trees because the balanced ones are weighted, are much more likely. That's the same setup, and now we can use analytic combinatorics in the same way to analyze the path length of binary search trees and get a comparison between, showing us the difference between these 2 models. Start as usual, but now we have permutations. And our cost is the length of the permutation. But now when we say IPL, we mean we want it's an IPL of a permutation, which doesn't make sense, except if you say that the permutation is what we want is the internal path length of the BST you get from that permutation by inserting it into an initially empty tree. Again, the number of permutations of size n is n factorial, and that saves us a step in the calculation, as you'll see. And the accumulated cost is the total IPL of binary search trees built from all permutations. So now our counting EGF is a simple one. That's the basic EGF for permutations. It's just 1 over 1 minus z. We have an n factorial involved, but that's our number of permutations, so that cancels out. Our cumulative cost EGF, it's the same symbols as before, except now we have permutations, not trees, and IPL has that different meaning. And so to get the expected internal path length of a binary search tree built from a random permutation, we're going to take n factorial coefficient z to the n in that, divided by n factorial, and those n factorials cancel out. So it's just it's treating it as an ordinary generating function, gives us the divide by n factorial for free. It's just a little calculation trick because we're using exponential generating functions, which means that we divide by n factorial. But our probability space is permutations, so we want to divide by n factorial. So it serves both purposes and saves us the step of dividing. We just look for the coefficient of z to the n and c of z. So next we have to look at developing a generating function equation for that c of z using the recursive definition of the binary tree structure according to the way that we construct trees. So same basic steps as before, it's just that we're going to come up with a different equation because we have a different structure. So again, this is just a summary. What we're after is a better equation, an equation that C of Z has to satisfy. And then what we're going to do is use this relationship that we talked about before that gives us all the permutations that lead to the same tree. And so that decomposition from a permutation P to a permutation that IPL of P is, those are all the permutations that give rise to that. And then IPL of P is got that recursive relationship as before. We can express everything there in terms of P sub L and P sub R because of this decomposition that we already talked about. And this one's even simpler than the other one. There's just one trick that often works with exponential generating functions. This PL plus PR plus 1 factorial causes, in the denominator, causes a little inconvenience in simplifying this formula. But we have Z to that same quantity. So what we do is differentiate to cancel out that one factor. Then you'll see there's a PL plus PR factorial on the bottom, and then we can mix that with the binomial coefficient. So this is a trick that often works with exponential generating functions. Differentiate, then cancel the PL plus PR in the binomial coefficient, and you're left with the PL factorial, PR factorial. And now you've got a very simple double sum that completely decomposes and separates. the P of ZB or P factorial is just P of Z, and P prime of Z is the one that takes care of PL over PL factorial is PL minus 1 factorial, so use this equation. And then again, we get a very simple differential equation now for the cumulative cost exponential generating function for path length in BSTs. The decomposition is important. It's got to be precise, it's got to be correct, but once you have that decomposition, you automatically get a relationship that the exponential generating function for the cumulative cost and the counting GF have to satisfy. And again, solving for C of Z gives, it's just simplifying that, substituting in for P of Z gives a very simple equation. So recognize that equation. We saw that in the first lecture, actually. That's the equation that came up with solving the quicksort recurrence. I guess it came up in the generating function lecture. Pretty much the same equation. So just with that observation, we solved that because it's a first order differential equation that has a simple integration factor and was not difficult to solve. So now we can summarize the analysis of expected length in a BST built from a random permutation on this slide. Start with the definitional equation for the cumulative generating function, substitute in the construction or the decomposition, differentiate to simplify, substitute to get further simplification, and that is a generating function that has the solution 2 over 1 minus z squared log of 1 over 1 minus z minus 2, 0, 1 minus z squared. And those are elementary series that we can expand to find the coefficients as we did before to show that the average internal path length in a binary search tree is asymptotic to 2n natural log n. So a log n as a factor, if you divide by n, log n to the average node in a binary search tree, square root of n in a binary Catalan tree. Since the same equation comes up, and people who've had algorithms courses know that there's a bijection between quicksort and binary search trees that explains this. We could have analyzed binary search trees just by taking advantage of this bijection. So that is, in quicksort, you have the first entry in the permutation is the partitioning element, and the smaller ones and larger ones are mixed. And then after the partitioning, you do them independently. And that's pretty much the same in a binary search tree. The first one is the root, and then you do the left and right independently. So you can show that the average number of pairs for quicksort is exactly the average external path length of BST built from a random permutation. And that's an interesting bijection to know and to take advantage of. Now this same approach works for a lot of other parameters of trees, and there's exercises to compute the number of leaves of trees and other things like that in the text. For finding the height of trees, it's much more intricate. It's a different approach because it doesn't break down really as well. But that's an interesting problem because it's a natural thing to want to know. What's the furthest node from the root in a tree? That tells us more information about the shape of the tree. So the height derivation is described in the text. And actually for both binary search trees and trees, height was an open problem for quite a while. So just to summarize what we know about the shapes of these two different tree structures, we looked at random binary trees and binary search trees built from random permutation. Those are typical shapes of those trees. The average path length, that's the average distance to a node in a random tree. For binary trees, it's square root of pi n. For BSTs from random permutation, it's 2 natural log n. And again, in the book, there's some description, although both of these derivations are quite intricate. The height now is known for random binary trees to be twice that average. And for random BSTs, it's a little more than twice. It's a constant times natural log n, where the constant is about 4.31. And again, there's lots of things that you might want to study about trees, and I know I've only really talked in detail about path length, but you can find plenty of examples in the book that show that the same approach works for many other tree parameters as well, and certainly don't have time to talk about all of them in this lecture. That's a summary of the study of path length in trees.